Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to talk about the cross product of two vectors. If you remember, in Volume 1 of Linear Algebra, we talked about the dot product of two vectors, which is one way to multiply two vectors, and we talked about that back then. I was saving the cross product of two vectors until now because you're going to find out that the stuff that we've been talking about with regard to determinants is actually very relevant to cross product of two vectors. Now I know that everybody watching this has probably dealt with this before in a physics course or maybe in a calculus course, but what you have learned then is all applicable and all true, but we're going to tie it into the linear algebra concept right here in a way that is going to be very, very useful for you. I remember when I first learned how to take the cross product of two vectors in 3 dimensions, the formula that they give you is very cumbersome, very hard to remember. I would never know how to remember that, but I'm going to show you a way here so that you never have to look up how to take the cross product of two vectors again. All right, so we're going to have the cross product of two vectors. Now, I know that you probably have seen this before. If I have vector A and I cross it with vector B, like this, then how you get that, the magnitude of A cross B, that's what I'm really calculating here, is the magnitude of vector A times the magnitude of vector B times the sine of the angle between A and B. Now let me draw you a quick picture because a picture is definitely worth 1,000 words in this case. Let's say that I have a vector. I'm going to call this vector A, pointed this way. And these are 3-dimensional vectors, so I'm doing my best to draw it on the board. It's not going to be perfect. Here's vector B. Now, these vectors exist in 3-dimensional space, and there is an angle between them, a direct angle between them that you call theta. All right? Now, what we say is, if we look at the length of A, that's magnitude of A, and we look at the length of B, that's magnitude of B, if we take these two magnitudes, multiply them together, and then take the sine of the angle that falls between them, then what we get is the magnitude of the cross product of those two vectors. And if I wanted to draw that vector, the cross product vector, it would be something like this. And I'll remind you of this in a second. Basically what this is A crossed with B, and it's equal to the product of the magnitudes and the sine of the angle between them. But the interesting thing is for the cross product is always perpendicular to the other two vectors. So that's kind of hard to see in a chalkboard, but basically, or in a marker board. Basically, if you have a vector pointed this way and a vector pointed this way, the cross product is always going to be perpendicular to both of those vectors. So think about it. Any two vectors I put, even in 3-dimensional space, if I put a vector here and then a vector pointed in a different direction, those two vectors will always lie in a plane. Any two vectors you pick, this way, or any two vectors at all, you can always put a sheet of paper that will contain those two vectors. The cross product will be perpendicular to that plane that contains those two vectors. In the board, I'm trying to draw it as a vector going this way and this way, kind of coming toward you a little bit and down, and then the cross product is perpendicular to each of these A and B vectors. And the length of the cross product is equal to what you get here. So when you learn it in physics, you do it with a bunch of drawings, and you learn that if you take the magnitude of A and the magnitude of B and you multiply them, and you also multiply by the sine of the angle between them, then what you get is the magnitude of the cross product. And most of the time in physics course, we kind of whitewash it a little bit and we say, oh, the direction of the cross product is just perpendicular to these two vectors, right? And you know that. You should intuitively know that the cross product of two vectors is always perpendicular to the two initial vectors. But what ends up happening is when you really sit down and have to calculate a cross product, the full vector form of a cross product, it can get a little cumbersome. So let me show you that. But before I do, I want to give you probably the biggest application of the cross product that you probably learned in physics, but I'm going to do it again here because I think it's cool. And also, it illustrates why you might actually use this. Okay, for an application. If you remember the concept of torque in physics, torque is a twisting force, if you think of it that way. When you have a bolt or a nut that you're trying to loosen and you put a wrench on it and you crank on it, you're trying to twist it about an axis. That force that you're applying through an angle is called a torque. You know, obviously you can push in a certain direction, you know, that's called a force. When you apply a force through an angle, that's called a torque. So it's kind of a twisting sort of force. That's really what we call torque. But in terms of physics, the torque, we have a fancy looking T, it's called a tau. and that's equal to the cross product of the radius vector times the force that you're exerting on the end of your wrench, for instance. So if your wrench is, 8 inches long, that's the radius vector, and the force that you're applying at the end of the wrench is, 2 newtons, then the cross product of these two vectors is going to give you the torque. The torque is going to be about the axis of rotation of that wrench, right? That's basically what's happening here. So for a picture, okay, I'm going to do my best. This is going to look a little weird probably, but here's a nut or a bolt, however you want to think of it, right? I'll try to draw it kind of big like this. And it's drilled into the board, and I'm trying to loosen it, all right? So what I would do is I would stick a wrench on that sucker and try to loosen it or tighten it. And so my wrench, and I'm not a great artist, but my wrench is basically going to look, you know what, let me switch colors. I like my wrenches to look different color. So my wrench might come out here and attach to here, and maybe I've got some jaws that kind of come out here and meet here, and then of course my wrench is about this long. I know it looks a little bit weird, but you can get the idea. You stick it on there and you want to either tighten it or loosen it or whatever, and you're exerting a force way out here at the end, and you already know from experience that you get more of an effect, more of a mechanical advantage, more torque if your force is at the very end. If you have a wrench that's really long, you're going to be able to loosen that nut much, much easier than if you have a really little tiny wrench. Not going to be so helpful, all right? And that's because you can see the F is right here. If you have or the R is right here. If the radius of the length of your wrench is larger, you're going to get a bigger torque, right? If your force is bigger, you're going to get a bigger torque. So anyhow, what we're doing when we do this typically is we're applying a force straight up and down. You also know that you really want to do straight up and down at roughly a 90-degree angle. That's kind of, you're going to get the most torque on your nut, right? So this is the force acting on the end of this guy here. And then the radius, we'll kind of draw something like this. The radius vector is going to be coming from there, right? So I'm trying to draw it, really you can kind of shift this up so that the radius goes and connects head to tail with the force vector, but you get the idea. So this is the radius vector. This is a vector, just like any other vector. Radius is a magnitude, that's the length and a direction. The force has a magnitude and also a direction. They're two vectors, and we're saying that the torque is equal to R cross F. Okay, R cross F. And you know from experience that if you angle this force perpendicular to the radius vector, you're going to get the best torque, right? And that is because if you look here, the torque, which is the cross product of A and B, is A times B. You know what, let me just rewrite it here. The magnitude of the torque is the magnitude of R cross F is the magnitude of R times the magnitude of F times the sine of the angle between these two vectors. Okay, I'm just recopying what we have up above because this is the cross product we're talking about in particular here. Right? Let me ask you, this is 90 degrees, sine of 90. What is sine of 90 degrees? It's 1, okay? So this entire torque calculation is really kind of dependent upon the angle. If the angle's 90 degrees, you get maximum torque. If the angle's less than 90 degrees, you always get less than maximum torque because the sine is going to chop it down and chop whatever you have here away. It's going to just chop it down to 0 even. In fact, if I were stupid and put a wrench on like this and decrease the angle halfway and started pulling at an angle like this, you know that I'm going to get less torque. And if I'm really dumb and I hold it like this so the angle between my force and my radius is 0 and start pulling it in like this or pushing it in like this, I'm going to get 0 torque. And that's because the angle in this case, if I hold it like this and start pulling with the force like this or like this, the angle between these vectors in that case would be 0, and sine of 0 is 0. All right, so I'm just trying to give you a little motivation. There's many cases when you would use the cross product of two vectors. This is one from, elementary physics when you're trying to take the cross product of two vectors. You get in the higher math, you deal with electricity and magnetism. The cross product of the electric and the magnetic field can give you the power of an electromagnetic wave. Cross products in mechanical engineering everywhere, cross products in chemical and in civil engineering everywhere. So this is kind of a general thing that you learn in physics. You have a drawing, you're taking the cross product, there you go. But the question is, or the statement is here, this guy is giving me the magnitude of the torque that I'm calculating, or the magnitude of the cross product. How do I find the full-blown cross product of any two vectors? Not the magnitude, the whole enchilada. How do I do that? Well, I'm going to teach you that right now. The cross product of any two vectors, notice I don't have any magnitude bars around this, so I'm calculating the full-blown cross product. And this is what I'm trying to lead up to here. Can be written as the determinant of a matrix, if you can believe that. Okay, and that's why I'm bringing it up. In the first row, the determinant of this matrix is going to be your unit vectors. That's the I, that's the J, and that's the K, right? Which is X, Y, and Z direction. All right. On the next row, you have your very first vector, vector A, the X component, the Y component, and the Z component. And then on the next row, you have vector B, X component, vector B, Y component, vector B, Z component. So basically what you have is, in order to calculate the cross product of any two vectors, if you look this up in a physics book, they're going to give you a very big, long formula of something you just have to plug it into, the different components in the different directions. But all of that can be written as the determinant of a matrix. And now you should know how to find the determinant of any 3 by 3 matrix. Notice this is a 3 by 3 matrix. Since we have 3 dimensions in this spatial, at least spatial dimensions, then it's very common to get 3 by 3 matrices like I was telling you before, because we live in a 3-dimensional world. Now, we're not including time. We're not talking about Einstein here. 4-dimensional space-time, that's different discussion for a different day. But for typical mechanics and things like that, we're always talking about 3 dimensions. So let's just cut to the chase. And let's say you were given on a test that your A vector was 3 in the I direction, plus 2 in the J direction, plus 4 in the K direction. This is X, Y, and Z components. And your B vector was just simply 1 in the I direction, plus 2 in the J direction, minus 2 in the K direction. All right, so these are the 2 vectors that you have, X, Y, and Z component of each one of them. And I ask you, find, well, let me switch colors. Find A cross B. Now, when I find A cross B, I don't want to get just the magnitude. I don't want to get just the direction. I want to know the actual vector, the X component, the Y component, and the Z component of that vector. Because in what you typically learn in Physics 1 is the magnitude of the cross product is mag A, mag B times the sine of the angle. In order to calculate that, I would need to find the magnitude of A. I would need to find the magnitude of B, which I know how to do with Pythagorean theorem. All right? But I would need to find the angle between these 2 vectors. Can you look at this and tell me what the angle between those 2 vectors are? Well, no. It's something you can calculate, something you can find from this, but it's not something that just jumps off the page. You don't know the angle between the 2 vectors readily, okay? So typically what you do when you find the cross product of 2 vectors is dispense with all that, and you just calculate the actual vector and so on of the cross product. So this is the way you set it up. Your first row is just I, J, and K. Cross product, the order matters. So the first vector has to be the vector A. 3, 2, 4. These are the components. Vector B is this guy. 1, 2, negative 2. You have to have them in the proper order because the cross product, the order does matter. Okay, so then we want to actually do this. How do we calculate any cross product, or I should say any, I left out one very important thing. This is the determinant of this matrix here. So A crossed with B is going to be the determinant of this. How do we do it? Just because there's I, J, and K here, don't be afraid of that. That's just a placeholder. So the way you handle it is you go across like we have always done. It's going to be I direction, and inside you cover this up and you cover this up like we did in the last section. 2, 4, 2, negative 2. So just to make it absolutely clear, I'll say it's I times the determinant of 2, 4, 2, negative 2. Okay. Now we have to go to the next guy, but we always have to remember to put our negative in here, and J hangs around front times the determinant of the matrix that's left over when we cover these guys up. 3, 4, 1, negative 2. 3, 4, 1, negative 2. Right? And then we have plus in the K direction times the determinant of whatever's left over when we cover these guys up. We have 3, 2, 1, 2. 3, 2, 1, 2. And this is basically how you are going to end up finding the cross product of these vectors. So in the I direction, you're going to do a crisscross. This will be a negative 4 minus, this will be a positive 8. The minus J hangs along for the ride. Here, this becomes a minus 6. And then we have a 4, so it's minus 6 minus 4. Remember, you go this direction minus this direction. Then we have plus in the K direction. This becomes a 6. This becomes a 2, going this direction like that. I think you can see where we're going. In the I direction, what we end up having, this is going to be negative 12. We have to keep the minus j here. This is going to be minus 10. And then we have the k direction. This is going to be 4. And then finally, we just rewrite everything in a typical way that we do for vectors. A cross b. This is negative 12 in the I direction. This is negative 10, but we have a negative here, so it becomes a plus 10 in the j direction. And then here we have 4 in the k direction. And this is the final answer. We have negative 12 in the I direction plus 10j plus 4k. All right, I know it looked a little bit weird, but think about it. The only work you did was between this step and this step to find this cross product. If you look in a book to tell you how to find the cross product of three-dimensional vectors, it's going to get the right answer, but it's going to be a bunch of plug and chug stuff. You'll never memorize it. You'll never memorize. You'll always have to look that up in a book somewhere, because that formula, all of these arithmetic here that's in this step, it's all blown out in a formula you can find in a book somewhere, but you'll never remember it. You can remember this, and that's why it's useful, because you know how to find determinants of 3 by 3. So if you just remember I, j, k, vector A, vector B, boom, find the determinant, everything else just falls out. One thing to keep in mind, the vector we get is this, and we know from the definition of the cross product that this vector is perpendicular to the plane that's contained by this vector and this vector. So if I got in three-dimensional space and I actually plotted the A vector, and in three-dimensional space I plotted the B vector, all right, then if I plotted my cross product vector, I know from the definition of the cross product that this vector lies perpendicular to the plane encompassed by these A and B vectors. You would never see that by looking at these components. I don't know by looking at it that it's perpendicular. Of course I don't, but I know what the definition of the cross product is. All right, we'll do one more. Vector A is 3j plus k, and vector B is negative I plus 2j plus 5k, like that. And we want to find the cross product, which is A crossed with B. All right, A crossed with B. It's going to equal to the determinant of the large matrix that has in the first row I, j, and k. Vector A has to come first because that's the first in the cross product. There's no I here, so you have to put a 0. You can't just ignore things. You have to put a 0 there since there's no x component. The y component is 3, z component is 1. Here you have a negative 1, 2, and 5. And then you just have to find the determinant of that matrix. So what you're going to have then is you go across the first row. First you'll have the I, then you have the determinant of the matrix form when you cross these guys out. So you have 3, 1, 2, 5. And I tell you, you get very good at it after a while. You have to remember the negative, then you put a j times the determinant. Cross this, so you have 0, 1, negative 1, 5. 0, 1, negative 1, 5, plus the k from this times the determinant of this, 0, 3, negative 1, 2, 0, 3, negative 1, and 2. And we all know how to calculate the determinant of these small matrices, so this is a hat here. I need to make sure I put those there. Then I hat, crisscross like this. 3 times 5 is 15, minus the 2 from this direction. The j is going to be 0, minus, this is going to give you negative 1, plus the k direction. This is 0, minus, and this gives you negative 3. This is extremely simple to find the final answer. 15 minus 2, well, let's just be explicit here. Inside here is going to give us 13, minus the j. Inside here gives us positive 1, and inside the k, this gives us positive 3. I could have combined steps, but we'll just make it here. 13i minus j plus 3k. 13i minus j plus 3k. And I know that this vector, if I look at it in three-dimensional space, is perpendicular to the plane that's formed by these two vectors. These two vectors will always lie in a plane. This vector is going to come out of that plane. The length of this vector is going to be equal to the length of this vector times the length of this vector times the angle that's formed between these two vectors in three-dimensional space. Of course, I don't know what that is. It's something I have to find, but it all goes into what the definition of the cross product is. I hope that you see the usefulness of this. If you don't see the usefulness of this, then you haven't taken enough classes where you have to calculate the cross product. Being able to remember how to find the cross product of two vectors without looking something up in a book is very, very useful. And so that's why this is honestly my favorite method of calculating determinants, is doing this kind of cross method and looking at the submatrices here. We call it expanding about the first row. And the reason is because obviously when you're finding determinants of regular matrices with numbers, it's useful to be able to know how to do that in your head, or at least not to have to look it up in a book. And when we're finding cross products of vectors, which is all the time in engineering and science, it's also used for the same thing. So make sure you understand this. Now, I hinted before that this was a subset of a broader, kind of more comprehensive technique. We're going to learn that in the next section. But no matter what you learn from here on out about the broader technique, really, I want you to remember this. I want you to remember how to find these determinants of 3x3s and how to find these cross products, because these things will be useful to you in all of your classes that you take from here on out.